Hi, everyone. My name is Gal Oshry. I'm a product manager at AWS, and I'm here to talk to you about training your machine learning models at scale. So machine learning has proven itself useful across a wide range of applications, ranging from recommendations to credit risk prediction, and from autonomous driving to extracting data from documents. Recently, there's been an explosion in large-scale deep learning models that are used in natural language processing and computer vision applications. On the left, you see a generated image of a living room from 2017 using a machine learning model. While you can tell that it's a living room, the picture is not very coherent, and you can tell that it's probably computer generated. Fast forward 5 years. In 2022, Stable Diffusion generates image like this of a very clean living room, where you'd have to actually look very closely at it to tell that it's not a real image. So how did this happen? First of all, there were notable algorithmic innovations, especially the transformer architecture, which is likely used in most of the large-scale models that you hear about today. The other side of this is that these models are getting larger and larger and using bigger data sets. It turns out that as these become larger, the performance of the models gets better, following a power law. While there are still discussions on the exact scaling laws, the takeaway is that at least for now, we can get better performance by increasing the scale. Okay, so training large models is awesome. Let's just turn that scale dial all the way up, and our models will solve all of our problems. Well, it's not that easy. There are quite a few challenges that I'll talk about. First, we want to be training on the latest hardware. There's continuous innovation, and every few years, the training performance increases by 2 to 9x. However, as with any large distributed system, there can be hardware challenges, and we need to think about health checks to make sure that the hardware is working correctly to minimize disruption. We also want to think about orchestration of this hardware and ensuring that the various components involved in model training are working correctly. We talked about needing to use large data sets for these models, and the various pitfalls in storing, processing, and loading very large data sets. Doing this efficiently can require significant development effort. Similarly, we need to think about scaling up the infrastructure as well as the training algorithms. For example, today's largest models don't fit on a single GPU. We need to think about distributing them across GPUs and figuring out how to continue training efficiently. Finally, we need to think about cost. Some papers share that the compute for training their large-scale models can cost at least hundreds of thousands or millions of dollars. We also want to think about how much time the machine learning team is spending fighting against infrastructure as opposed to exploring model improvements, which is their main focus. Many customers tell us that the machine learning team's time is the most valuable resource, and the number one priority is ensuring their time is spent efficiently. But not all hope is lost. We'll talk today about how SageMaker can help. SageMaker provides many capabilities that help machine learning engineers and data scientists train models at scale. At the bottom layer, we have the infrastructure, where SageMaker provides easy access to the latest and broadest suite of hardware, including NVIDIA GPUs, AWS Trainium, and fast networking between instances. The layer above that focuses on the infrastructure management and tooling capabilities that SageMaker provides. It easily enables large-scale cluster orchestration, including running health checks on GPUs. If a job fails due to a GPU error, SageMaker can reboot or replace that instance based on the type of failure that it sees, and start the job again automatically. This makes a huge difference in reducing the interruption time and removes the need of manual intervention at 3 a.m. when something goes wrong during the training job. SageMaker also provides tools for debugging, profiling, and tracking your machine learning experiments, and I'll share an update on that in a few minutes. There's also an automated model tuning to help you find the best hyperparameters. Across all of this, SageMaker ensures that customers pay only for what they use. And at the top layer, we have a set of libraries and frameworks that are optimized for AWS, including TensorFlow, PyTorch, and Hugging Face. There's also a set of SageMaker distributed training libraries that offer significant performance improvements and make it much easier to get started with distributed training, for example, with data parallel and model parallel. But it's worth noting that you're always free to bring your own libraries to SageMaker, such as DeepSpeed and Megatron. SageMaker provides you full flexibility for your training, and you can choose which tools or libraries you want to use. Now, I've told you about the benefits of SageMaker training jobs, but I haven't really explained what they are, so let's talk about that. Now, to train a model, we want some compute to run our training code on some data. It will also output the final model, checkpoints, and metrics. And this is exactly what SageMaker training enables. When you start the training job, it spins up a cluster of instances of your choosing over here. It downloads your image from Amazon Elastic Container Registry or newly released from third-party registries. It then loads the data from S3, but it can also use EFS and FSX for Lustre, and it starts training your model. It will then sync checkpoints back to S3 during training. It will store your metadata and hyperparameters in the SageMaker control plane, and it will stream the logs to CloudWatch so you can view them during or after the training job. At the end of the job, it will store the model in S3 and spin down those instances. And this is critical. We talked about cost earlier. It's not ideal to pay for a large cluster of expensive GPU instances if they're not being used. And an added benefit here is that if the job fails overnight, it will auto-stop the cluster. But alternatively, if your training code is resilient and can continue from a checkpoint, you can set it to auto-retry instead of waiting for that manual intervention. So here's the most important code for converting your existing model training to a SageMaker training job, the estimator API. At a high level, the cifar10.py file is very similar to what I would use if I was just training on my laptop. I provide that to the estimator API along with the instance type I want to use, how many instances I want, and the hyperparameters. Now, I can easily make changes to these later on to try different experiments, either with different instance types or changing the hyperparameters themselves. I then provide metric definitions, like the loss, to tell SageMaker I want to track that metric from my output logs during training. I can view it in CloudWatch during and after the job. Finally, I call estimator.fit with a path to my data in S3. Now, the good news is that we recently made this even simpler. You can write your code to train the model as if it was running locally on your laptop, in a notebook, or in SageMaker notebooks in Studio. You can then add the Python decorator remote to that, and it will automatically take a snapshot of the variables, functions, packages, and other runtime, serialize them, and submit them as a SageMaker training job. Once the job is started, you want to keep track of that experiment. Now, unfortunately, there's a tendency for machine learning teams to do this in spreadsheets or even docs manually, and this makes it difficult to replicate past findings quickly or communicate results with teammates. With SageMaker, that metadata about the training jobs is kept automatically as soon as you start the job, and you can view it in the AWS console or through the APIs. Having this done automatically and consistently across the team is really useful. You can even go and clone the job to restart it with the exact same parameters and make sure that the experiment reproduces. Expanding on the theme of experiment and metric tracking, we recently launched Hosted TensorBoard. TensorBoard is a data and experiment analysis visualization tool that is popular among deep learning researchers to understand how their experiments are going and to debug things when things aren't going right. TensorBoard is traditionally run by logging the data to a folder and then starting the TensorBoard web server pointed at that folder. But with the SageMaker hosted TensorBoard, you don't need to configure TensorBoard every time. You can set it up once and then go to the Manage TensorBoard interface to look at your different training jobs and view the TensorBoard data for them, analyzing them in a scalable and secure way. I want to now talk a bit about the SageMaker distributed training libraries that I mentioned earlier. A really cool example of their use is that LG trained Tilda, an AI artist that created 3,000 images and patterns for fashion design. These were used in last year's New York Fashion Week. The models were trained using the SageMaker distributed training libraries, and they were able to train the model 59% faster with pretty minimal code changes. A recent addition to these libraries is the integration of sharded data parallel and tensor parallel techniques. Now, sharded data parallelism is a memory-saving distributed training technique that splits the state of the model, gradients and optimizer states, across GPUs in a data parallel group. This enables fitting larger models or increasing the batch size using the freed-up GPU memory. Tensor parallelism is a type of model parallelism where tensors like the model weights are split across GPUs. Together, these techniques can be helpful if you need to reduce the global batch size, for example, if you're training on a very large cluster and might be seeing some convergence issues. You can enable these features in the SageMaker model parallel library by setting the sharded data parallel degree and the tensor parallel degree parameters in your PyTorch estimator. I want to wrap up by highlighting an exciting recent announcement. The Technology Innovation Institute used SageMaker to train the Falcon model, which at this time is at the top of the Hugging Face Open LLM leaderboard. They used SageMaker to construct a trillion token dataset with CPU jobs to deep duplicate and filter the data. For example, they used ML classifiers to filter profanity. They also built an automated monitoring solution using Amazon CloudWatch to monitor the GPU, CPU, and memory utilization during the training jobs. If any of those metrics fall below a threshold, an alarm is triggered, and the team is notified, and they can act on it. The model Falcon is also available in SageMaker Jumpstart, so you can actually get started using it immediately today. I want to share a couple of helpful links for getting started with SageMaker and learning more, and especially I want to highlight the bottom link, which is a blog post about the best practices for training LLMs on SageMaker. It can be really helpful if you're getting started and want to kind of see what you need to do to get the best results with training these large-scale models. Thank you very much for your time today.